Good day to you from Chem Help ASAP. Let's see what MO theory data look like. On the screen is methane. We'll analyze methane through MO theory. There are two main types of MO theory that are applied to molecules. One is semi-empirical and the other is ab initio. We're going to use semi-empirical because it's just a bit easier to analyze. Methane has 5 atoms, 1 carbon and 4 hydrogens. Together, these 5 atoms have 8 valence atomic orbitals, 4 from carbon and 1 each from hydrogen. In a semi-empirical calculation, the computer program takes these 8 AOs and generates 8 new MOs as an output file. For each new MO, the output will list the contribution of each AO in making the new MO. The output will also predict the relative energy of the MOs. Let's see some real output data. Here is an output file, at least part of one. Going down on the left is a list of all the atomic orbitals that were used in the calculation. Going across the top is a list of the 8 new molecular orbitals. 8 AOs in and 8 MOs out. There are several things to notice here. Thing number 1, this is messy and complicated. This doesn't look like hybridization. It's not. It's different. Thing to notice number 2, the energy of each new MO listed in electron volts is at the top of each column. MO number 1 is lowest in energy. MO number 8 is highest. Negative energy is lower, more stable. Thing to notice number 3, each new MO potentially has contributions from each of the AOs on the left. The contributions are represented by numbers in the columns. These are coefficients. The coefficients can be positive or negative, and bigger values, positive or negative, mean larger contributions. Therefore, each MO is a linear combination of the atomic orbitals in the molecule. We saw this idea of LCAO in a previous video. Okay, do you remember from the previous video that hybridization, with its equal 4 sigma bonds for methane, isn't consistent with the excitation data for methane? Methane's excitation data show that methane's valence electrons have 2 different energies. Does MO theory do better? Methane has 8 electrons. These 8 electrons fill 4 MOs. That means MOs 1, 2, 3, and 4 are filled. The other orbitals are empty or vacant. MO1, so let's look at these energies. MO number 1 has an energy of minus 28.9. MOs 2, 3, and 4 are all the same at minus 13.3 electron volts. MO theory indeed does predict that the 8 valence electrons of methane are at 2 different energies. That doesn't mean MO theory is right, but at least it seems more consistent with the experimental electronic properties than hybridization. The output files generated by MO theory provide coefficients to connect the contributions of AOs to the creation of new MOs. MO theory does a much better job of making reactivity predictions than hybridization.